Hello, I'm thrilled to be here for TEDx at NITKSurathkal, and I'm Viral Shah, creator of the Julia language, one of the creators of the Julia language, and also co-founder and CEO of Julia Computing. We started the Julia project in 2009, and I had three co-founders back then: Professor Alan Edelman at MIT, and then Jeff Bezanson and Stefan Karpinski. And we started out saying, hey, we want to solve the two-language problem. As scientists, the two-language problem was really frustrating for us. Having sort of a programming language that was simultaneously as easy as Python or R and as fast as C was essential in our journeys as computational scientists. And this is what got us sort of thinking, like, hey, something like this doesn't yet exist. Can we try and put that together? Back when we started in 2009, it was almost believed like a law of physics that that this is simply not possible. And we gave it a shot. In 2012, we announced Julia to the world. In 2015, we set up Julia Computing because we started seeing companies beginning to use Julia. And here we are today with what I believe is a 1 million strong community of Julia users worldwide. I did all my work on Julia, at least in the early days, out of India, out of Bangalore. And while I was working for the government of India on its Aadhaar project, and it was truly some of the most interesting times for me working on Aadhaar and with the government machinery in the daytime, and spending my nights on hacking a programming language. For the first 3 years, it was just the three of us, and it took a long time. Three of us programming, and it took a long time to get to a system that was really compelling. But in 2012, when we announced it, we wrote this blog post why we created Julia, and it got the internet fired up. It got people excited, and they joined us in our mission. We got 100 contributors in the first year in 2012 itself, and today Julia has over 1,000 contributors, 5,000 packages, 25 million downloads. I mean, the stats are off the charts. So the question is, you might be wondering, how can a programming language really heal the planet, right? And let me say, let me describe how. The reason why a programming language matters for solving some of the biggest problems that face us is as following, right? We have a pandemic that is going on. We need to find a new drug. Our climate is warming, and we need to figure out how to control our temperature rise. Electrical vehicles are being put on the road by they're replacing old fossil fuel burning vehicles. You need new battery technology. You need new battery chemistry. We are looking at sort of all these different problems, right, that face us, and science is a key part of the answer, and computation is really a key pillar of science, right, along with theory and experiments. And this is where sort of all of this comes together, right? That if I, as a programming language designer, as a computational scientist, can build tools for the climate scientist, who is then building tools for a policymaker or a politician, you can really sort of see the pieces coming together, that your climate simulations need to run really fast so that you can iterate on many of these models. You can try out different models. You can try machine learning. You can try all these new ideas in order to figure out if you have the right model. And then once you run enough numbers of models, you get insight into what's happening. Now, in order for this climate scientist to be productive, what do they need? Well, they need tools that make it easy for them to compute on their models. They want to spend as little time writing their programs and as little time running their programs. Writing their program is strictly human time. It's what you type into your editor and your code. Whereas running time could be on your laptop, or it could be on a supercomputer, or it could be on a Raspberry Pi. But in all cases, all of us will agree that the lesser the running time, the better. And so this is how, in a nutshell, if that in a nutshell, how I think of my role as a programming designer, as a computational scientist. I'm helping scientists come up with the kinds of discoveries and inventions that will actually solve some of the world's most difficult problems. Now, I've talked a little bit about climate, but the same applies to drug discovery, or discovering new batteries or new chemistries, and really sort of any kind of scientific problem that scientists are trying to solve. So what is it about Julia that makes all this possible, right? There have been so many programming languages along, for all these years. So why Julia and why now, right? And there are many parts to this answer. In the past, like I said, right, we had the two language problem. So you had either languages like MATLAB, Python, R that were easy to use, but they were not high performance, or you had to use C, C++, Fortran, Java if you wanted performance, but then, you had to write 10x more lines of code. And this really boils down to, to computer language design, right? That can you design a language that can do both these things? And the answer is that if you pick the right underlying technologies, if you design it right, you can actually get quite far with very little. And this is where sort of Jeff, Stefan, and myself were able to get quite a good working system for the first 3 years as we worked on the project. But then it was really sort of the community that came over and really sort of made Julia into what it is today, the thousands of programmers out there. So let me show a little bit of a demo here, right? Just so that you know what I'm talking about. And there we go. All right. So there's, there it is. I've started Julia 1.7, and that's a development version of Julia as of today morning from GitHub. And I go 1 + 1 and it's all good, and I can go and generate some random numbers, or I can create a 3x3 matrix, or I can create a normally distributed 3x3 matrix, and so on and so forth, right? And I can assign it to something, and I can add matrices, all the usual kinds of things that if you're a user of NumPy would be very familiar to you. However, now let's do something more interesting, right? So what is it that makes a programming language fast? And what does it mean to run fast, right? Well, programming language, a program is probably going to be fast if you generate the right underlying assembly code, right? If you generate tight assembly code, you expect the program to run fast. Now, Julia can actually let you see what's the underlying assembly, right? So let's pick the very simple version of, let's just see what's happening with 1 + 1, right? Nothing much is going to happen here, but we can actually see what's, what the generated assembly is. Or let's write a function, right? If we write let's say f of x comma y equals x plus 2 times y, okay? I can now go and ask Julia to show me the code that it generates for a function that is trying to, apply this to 2 input arguments, 1, 2, and so on and so forth, right? So you can see that, you can actually get your hands on this assembly that is generated in Julia. And now you might wonder why is it, what's the special, sauce that makes Julia so fast? And, what is it about its design? So one of the things that's really nice about Julia is the design is centered around multiple dispatch, right? So if you're used to object-oriented programming, you might think that, you might know that dispatch, it's single dispatch, right? You pick a function a method is picked for execution based on the type of the of the first argument often, or on the object that you dispatch it on. In multiple dispatch, it depends on all the different input arguments that you give. So for example, I can ask Julia, how many different plus methods do you know about? And Julia comes back with the answer that in this Julia system, there are 190 plus methods that have been designed, that have been defined by all of us together. And it can add, not only numbers, but, big integers and dates and matrices and all kinds of stuff. And so this is what really makes Julia a powerful system. The multiple dispatch is a great match to the mathematics. It allows you to write very clean and well-separated code, while at the same time giving the compiler enough information to actually generate, tight assembly that gives you very fast execution. So this is in a nutshell what happens underneath Julia, right? And if you're familiar with LLVM, then you can actually go and look at the LLVM that is generated before the assembly, and so on and so forth. And you can actually ask Julia, hey, what is the code native of more complex things, right? Like maybe like the sum of a matrix, for example. And Julia will just kind of go and print out everything. If you're an assembly programmer, you'd like to read that. But this is not a primer on writing assembly code, so I digress. But I hope I have made the point about how programming language design can lead to fast code that will help the climate scientist, who will then be able to run multiple simulations and come up with recommendations on, hey, how much carbon dioxide emissions do we need to reduce in order to restrict the the temperature rise to a 1 degree or 2 degree global average. And this is really what sort of computational science is all about. And I feel thrilled that I've actually been able to be part of this. I've been on this journey. Let me show a few other things while I'm at this, right, about what makes Julia what it is. So here's the Julia GitHub page. Well, let me say, okay, there we go. And here's what we have. Here's the Julia website, right? So if you're interested in Julia, you start out here. And I have dark mode, so it looks a little different, but you can see sort of everything that's going on in the Julia community. It's quite a large community. But then all the action on the Julia language happens on GitHub out here. And there are over 1,077 contributors who have actually written at least one line of code that has been accepted into the Julia project. And you can see that it's a living, breathing open source project with all these many issues and pull requests. And then, we have a fantastic community, fantastic documentation and so on and so forth. There's a brilliant community out there. And I would invite you all to come and engage with us, talk to us, and really participate in sort of developing the kinds of tools that the world will use in order to solve some of these, these challenging problems. So, this is, for example, a list of all the Julia organizations that are out there, right? Each one of them has their own logo and their GitHub organization. So if there is a particular kind of computation that you'd like to do that is not yet available in Julia, that is a great place to get started. We have a very welcoming community. So, if you're learning Julia, you check out the learning section. But then once you kind of teach yourself some Julia based on all the materials here, I would suggest joining onto the community. Come on to GitHub, discuss on discourse, or join the Julia Slack. And I believe that one of TEDxNITKSurathkal's own graduates, Shashi Gowda, is one of the Julia core contributors who got started in exactly this way. We met him through Julia's Google Summer of Code, and he joined on GitHub and discourse and Slack, and everything was sort of, he became a core Julia contributor very early on, and Shashi is now pursuing a PhD at MIT. So this is a bit of a primer on Julia and the community and the way we are sort of doing interesting things and solving problems. I would love to point out one more thing before I sign off, which is the SciML ecosystem in Julia. So, everyone is familiar with machine learning and how machine learning has really made it easy for us, has solved problems in computer vision, in speech, in natural language processing, in all these different areas where it was very difficult to make progress in computer science for so many years, for so many decades. There is a branch of machine learning called scientific machine learning, which is being driven by the Julia community, where you take the data-driven machine learning, like your computer vision algorithms or your neural networks, and combine them with scientific phenomena. So data-driven machine learning often does not know about the underlying physics or the science inside of a problem. However, we understand, Newton's, laws. We understand the equations of motion. We understand the dynamics of various systems. And if only we could combine these two things, right? If we could combine the knowledge that we gain from data with the scientific models that we already have, and if we could have these two things sort of build on top of each other, that the data improves the models and the models improve the data, that is something that the scientific ML ecosystem in Julia is striving to put together. This organization is led by Dr. Chris Rackauckus, who's also at MIT, and a number of contributors who are working with him. And the SciML website is a great place to get to learn more about the project and get started. So along with fantastic documentation, we also provide challenge problems, a place for the community to join in, and all the source code and everything else. So this is sort of what Julia is, the Julia community is all about, right? Like we love having high performance. We love having easy to use code. We love pushing the frontiers with things like scientific machine learning, and eventually actually going and solving real problems. So for example, I started out by talking about climate change, and here's the Clima project with the Oceananigans Julia package. It runs on GPUs. Julia is one of the few languages that runs natively on GPUs. And here you go. You can actually look at this ocean model, and there are beautiful videos and visualizations that the Clima team has provided, and you can kind of look at the source code out here and see how every little thing that we discussed in the design of Julia, in how it was put together, how the community comes together. You can kind of see it all coming together in this package. So here for example, one of the things I often like to do is check what a particular package uses. Oceananigans depends on all these other Julia libraries that have been built by hundreds of other contributors, and it all comes together for our climate simulations. So this is something I wanted to share with you. That's something that we started off, a small seed that started out as a scratching an itch to try and solve the two language problem so that scientists would be better off, has led to this amazing ecosystem of contributors, packages, and just new frontiers in science. And I would hope that you will find this useful. Maybe you get motivated, join the Julia community, and make some contributions yourself. Thank you so much for listening to me. Bye.